Good morning, everyone. My name's Doug, and I'm going to be talking about doing database read caching with Optane persistent memory. So normally I'm in California, but today I'm talking from New Zealand. So I'm going to be talking a little bit about Optane persistent memory, app direct mode and memory mode, and some work we've done on that. I want to spend a lot of time covering some benchmarks. I wasn't sure whether this was going to be a nightmare. It turns out it's a dream, which is good news. And then we're going to see how we can apply this to database read caching. And very happy to answer questions at the end. So this is blatantly an Intel marketing slide, but I'm doing it for two reasons. We're looking at a memory hierarchy. Since the first computers, there's been a memory hierarchy because there's always some points which have faster or lower latency, which tend to be more expensive, and the cheaper media is slower. But what I especially want to point out is Intel Optane persistent memory is absolutely dominating this space. That's just a reality. One other thing I want to point out is the latency times. When we start looking at the benchmarks, these will become more relevant. So just remember Optane persistent memory, just under a microsecond, DRAM about 0.1 of a microsecond. So if you remember those numbers, when we look at how we do database read caching, those numbers become more relevant. So for the last 40 years or so, all databases tended to persist data as files on the file system, be it on spinning disks, newer SSD drives, solid state, or the newer non-volatile memory. So everything was persisted on disk, and the data was loaded as needed into memory. So that's how databases have traditionally been used. This isn't a memory conference, so we're going to look at different aspects of that. So one approach to using in-memory persistent memory is to add persistent memory to the storage hierarchy. So persistent memory as a technology is relatively new, and Oracle Exadata last year released product software and hardware which did exactly that. So that's one way of using persistent memory to speed up storage. Another way of doing it is perhaps you could use persistent memory as the buffer cache to make loading data faster. That's one way of doing it. I'm not going to talk about that. I'm going to talk about doing the database all in memory. So you completely get rid of the buffer cache. So we're talking about using all of the data in memory and using persistent memory to cost effectively extend the memory, the DRAM. So when you have all of the data in memory, it gives you really fast data access, but there's downsides. If you have lots of data, you've got to have lots of memory. So that's where persistent memory can help. So you obviously need lots of memory, but DRAM's expensive. We also want to be able to do fast loading and unloading of the data. So persistent memory, on the face of it, can help you in many different ways. You can have larger capacity, it's cheaper, and you can get faster reads and writes, either direct read persistent memory or via storage technology. But Grady Booch had a famous quote, "A fool with a tool is still a fool." So the point is, you got to figure out what you're doing and why to take best advantage of this technology. So when I talk to some people about persistent memory, they think it's magic, but it's not. You got to understand the limitations. It has higher capacity, but it's still finite. It doesn't work everywhere. It only works on the latest second generation Intel Xeon CPUs. As a developer or architect, you still have to make hard design choices. And even though it's cost effective, it's certainly not free. So I'm going to look at two experiences where Oracle's in-memory database called times 10 used persistent memory. First, an app direct mode. We did a prototype back in 2018 when Optane persistent memory was in alpha. And just recently, we've made persistent memory in memory mode generally available. So persistent memory really has two modes, actually three modes. In app direct mode, you have persistent memory. It's byte addressable, but you need to explicitly design for it. In memory mode, it's still byte addressable, but surprisingly, it's non-persistent. But the nice thing is it just works. So another way of looking at it, in app direct mode, you make explicit design code choices whether to use persistent memory or DRAM. In memory mode, you just use memory, which makes things really simple, but you don't actually know whether you're using persistent memory or the DRAM as a cache. And we're going to drill down into that aspect. So fundamentally, as a developer, as an architect, you need to make best use of persistent memory. You need to decide which of your objects and data structures you should use in direct mode, memory mode, or both. Because it turns out with Optane persistent memory, you can choose how much memory is carved up for direct mode, memory mode. So you can actually have both. You can have all direct mode, or memory mode, or some combination. So the example I'm going to be giving is using the Oracle times 10 in-memory database. So times 10 is a relational database that has ACID transactions. So you commit, you roll back. So you use SQL or PL SQL to access the database, and the entire database is in memory. Because everything's in memory makes it really fast. But we're not crazy, we still persist the data to files in the file system. So it's recoverable if you lose power or have a hardware failure. And obviously it's highly available, and we have various ways of doing that via replication or clustering. So the whole point of times 10 is to be as fast as possible. And as such, it is the fastest Oracle database. It's also faster than all the popular relational databases and NoSQL technologies. So as an example of performance, I'm going to be talking about latency and throughput. So in this case, I'm using the latest version of times 10 with Intel Optane persistent memory in memory mode. So doing this SQL select based on primary keys, we're doing that in just over a microsecond. And we're going to look at under the covers to see what's really going on there. So a primary key lookup takes about a microsecond. An update takes longer because it does ACID transactions. We need to be able to deal with the redo and undo. So there's more going on under the covers, so it takes longer. So this was performed on a Intel Xeon Gold CPU going at just on 2.3 gigahertz. So we just saw that times 10 gives very low latency. So that's a single connection running on a single core that goes fast. If we run it on multiple machines, we get scalability. So in this case, we're running it on 64 machines, and we're processing just over 153 million ACID transactions per second. So most databases dream of going, a tenth of that speed. So this was doing 20% updates. So ultimately we were IO bound because we still had persist everything to storage. When we did a 100% read workload, we're doing just over 1.4 billion SQL lookups per second. So this was about 3 years ago. So with newer hardware, it would tend to go faster. So once again, we were using 64 machines in a clustered or grid configuration. So these are SQL benchmarks doing ACID transactions. How does it compare to NoSQL databases? So Yahoo had this problem many years ago. So they invented their own benchmark to compare various NoSQL technologies. So it's the Yahoo Cloud Serving Benchmark, or YCSB. So it's a throughput benchmark. So you want to maximize the throughput, this number here. You can use as many nodes as you need or want, and they can be using any hardware you want. So you can throw hardware at the problem, but that only helps if your product scales. So Cassandra has very good throughput, scales well, but it needed 32 nodes to do just under 250,000 operations per second. I'm not saying transactions per second, because most of these things have eventual consistency, which is a fancy word for a random number generator. So as you go down the list, you get faster throughput. You know, Aerospike did pretty well. They did 1.6 million operations per second in a cluster with 8 nodes. With times 10, we only needed 1 node to go faster. So that's nice. So that allows us to do more with less. But what if we added more nodes to times 10? So same benchmark, as we add more nodes, the throughput goes up. So about 3 years ago, we were doing 38 million operations per second. Under the covers, we actually implemented it in JDBC. So we did SQL selects and updates. So we implemented a NoSQL benchmark doing SQL under the covers with ACID transactions. So we were actually doing more work, but we had far higher throughput. Go figure. So this was all done on a product called times 10 Scaleout. So it's using the times 10 in-memory database. So there's a single database, but it's run on many machines. In this case, each machine was running a single instance. So it's a clustered database, which has shared nothing. How do you program it? You just use your favorite language, use the Oracle APIs. So if you know how to code against an Oracle database, it's the same for times 10, just change your connect string. Where does it run? Pretty much anywhere. So it can run on bare metal machines, your favorite VMs, or in containers. So it runs very nicely in Kubernetes. We have an operator for that. So pretty much runs anywhere in your favorite environment. So it's a SQL database. Just very quickly, here's some example of the sort of SQL you can do. We're doing a join here. It's a write outer join. And we're doing a roll up. So we've got a cube. So you can do analytic type SQL. Here's an example of using a with clause. And we've got an inner join, and we're doing partitions over. So you can do analytic type SQL, but it's really a transactional database. It's a row store. So if you need to do heavyweight analytics processing, that's where Oracle in memory is a far better solution. So that was a little bit about times 10. So I just want to cover now how we've used persistent memory with times 10. So we had some goals we wanted to make. 2 years ago, before Optane persistent memory was generally available, before the beta, we got some access to this hardware from Intel. So we wanted to see if we could do multi-terabyte databases on a 2-socket machine. And we wanted to load multiple terabytes of data significantly faster than the fastest NVMe storage. We wanted to do faster writes, but more importantly, because it was a prototype and we had only a couple of months to do it, we wanted to minimize the code changes. So it turned out we achieved all our goals. We're able to do 2.75 terabyte database on a 2-socket machine with 3 terabytes of persistent memory. We were able to load that database into memory in just over 44 milliseconds. So the important thing to compare that is, if we were loading it from disk, from files using the fastest NVMe storage, that would have taken us many minutes. So it gave us faster load time. And we're also able to do really fast synchronous write to disk. So I'm not talking about how fast can you do a a write to persistent memory, that's whatever. I'm talking how fast you can do ACID transaction, which involves many different operations. So it was a lot faster. So we developed that, the prototype worked, and we're waiting for a new feature of persistent memory called EADR, which basically guarantees if you lose power that everything from the CPU, L1, L2, and L3 caches will get persisted to persistent memory before you lose data. Because as it is today, you might lose transient data before it's hit persistent memory. So that's upcoming. So I've talked about app direct mode, where you need to explicitly decide how to use persistent memory. There's another mode of persistent memory called memory mode, where you don't need to care about complicated things like that. You can let it do it all for you. So it's basically based on the principle that not all data is created equal. You tend to get some data that is accessed more than other data. So you tend to always have some amount of hot data and cold data. The ratio of hot to cold data will depend, but that just tends to be a thing that's been around for the last 40 odd years of computing. It's really independent of technology. Now, according to the Intel marketing, they have a built-in memory controller which will automatically migrate that hot data to your DDR memory, to normal dynamic memory, and the cold data will tend to get migrated to the Optane persistent memory. And this will all happen automatically. So that sounds good, but how well does it actually work in practice? So I did a bunch of benchmarks to try and figure that out. So you need some hardware to do it. So we got some machines, they just happen to be super micros. So we've got 2 CPUs, but more importantly, we've got lots of memory modules. The more the better. So this was the model we used. So the point was, we have a 1 new machine with 2 CPU sockets. So that tends to be the sweet spot for computing because it's fast and it's relatively cheap. So we just happened to use this model of CPU. We had a couple of machines, so we ran it with multiple versions of Linux so we could certify it. Now, more specifically, we had 384 gigabytes of DRAM and 1.5 terabytes of persistent memory. So that gave us a DRAM to persistent memory ratio of 1:4. So that's important. So depending on your motherboard and the memory chips you buy, is it a 1:4 ratio, 1:8, 1:16? It depends. So this example was using a 1:4 ratio. So you plug in the hardware and then you use software to configure it. So I'm showing how I'd configured it. So I set this up with 0 app direct mode. So that meant all of the memory was used for memory mode. So I got 1.5 terabytes of data there. So if we look at the topology, I got 12 slots all running DRAM. They were using 32 gig DIMMs because they tend to be the sweet spot for cost effectiveness, which allowed me to use 12 other slots for persistent memory. So these are 128 gig memory modules. There's also 256 and 512 memory modules available from Intel. So you can have, higher capacity. But the important thing is I have the same amount of slots of DRAM as persistent memory, which allows me to have the caching effect. I've got lots of slots, which allows me to maximize the memory transfer throughput. So we've got some hardware. Now we're going to look at a workload I wanted to look at the simplest workload possible, which was still representative of a customer workload. So this is something we got from customers many years ago to dealing with virtual private network infrastructure. So the point is we've got a table with a primary key and some columns. So I took that table and I inserted 1.4 terabytes of data. So based on the width of the table, that had ended up being about 160 million rows. What's the workload? I'm doing primary key lookups and updates by primary keys as ACID transactions. I tested this using a C program with ODBC. It's an existing program we had. So it was multiprocess. We did fork and exec. It obviously also works with pthreads, works with JDBC, whatever your favorite API is. So when you run it, because it's multiprocess, that means each connection or process has its own PID. So I'm running it, and you can see each process is attached to the virtual memory of the ×10 database. You can see that's 1.4 terabytes. Each of those processes is going flat out, so it's consuming all of the CPU, and this benchmark has been running for a while. So when it's going fast, you should be minimizing your context switches and going as fast as possible. So there was a little bit of swap going on. I'll talk about that. There's a little bit of CPU wait. I'll talk about that. So fundamentally, you have to ask yourself, how much PMEM is actually being used? If you're doing app direct mode, you explicitly say, this pointer is accessing persistent memory and this pointer is accessing DRAM. So you're in control. But when you're using memory mode, it's not always obvious how much memory you're being used. So why this matters is, with persistent memory, it can be up to 3 times slower than DRAM. I'm saying up to because it depends. When you're using memory mode, you're always using DRAM as a cache for the persistent memory. So obviously the larger the proportion of DRAM to persistent memory, the more efficient the caching is going to be, but it costs money for DRAM, so it's a trade-off. Now with your system, if you're lucky enough that your working set size is smaller than the DRAM, then you may not be using persistent memory at all. And I say probably because it depends. If your working set size is really large, like it takes up all of the memory machine, because the working set is larger than DRAM, you're going to be using some proportion of persistent memory. So it's going to depend. So what that means is the working set size of your running application will tend to determine the proportion of persistent memory being used. So to find out how efficient this is, I came up with a series of benchmarks where I varied the working set size, and then I measured the latency and throughput for reads and writes using the ×10 in memory database as the application. So there's lots of probablys going on here. I don't like magic. To figure out what's happening, you really need to look under the covers and look at the CPU hardware events to figure out what's actually going on versus what you think is going on. So there's a system call you can use to figure that out. There's a command line tool that you can do, but what I used is a really cool utility which uses Grafana called Process Counter Monitor. So it's looking at those CPU hardware events, it's capturing them in Prometheus, it's displaying them in Grafana. So that means I can graphically in real time figure out what's going on. So by looking vertically, I can correlate things. So in this case, I'm looking at dynamic DRAM reads and writes and persistent memory reads and writes for each CPU. We can also look at what's happening over your UPI channels, there's all sorts of goodies. So this is just a screenshot. It's about 8 screens deep. So it's not the nicest user interface, but it certainly has a lot of cool and useful information. So by using this tool, I could figure out what was actually happening under the covers for the memory manager and how much DRAM was being used versus persistent memory. Without this tool, I would have been blind and it wasn't obvious what was going on. So this tool certainly helped me. So this is open source, anyone can use it. So I used 1.4 terabytes of data for my database, but I had 1.5 terabytes of memory. Why did I use 1.4? I actually started out using 1.5 terabytes of data in my database, and things worked, but I looked at top and I saw there was lots of swapping going on because I'd forgotten that the Linux kernel and the file system buffer cache still need memory to work. Likewise, my C programs to run the benchmark. So they needed their own memory to get stuff done. Because I'd used all of the memory for the database, these guys were forced to swap, which obviously made things very slow. So I arbitrarily made it 1.4 terabytes for the database, leaving some memory for Linux and my programs, and everything went a lot faster. So there's nothing magical about 1.4. It's just the first number I tried and it worked. So the point is, almost all of the persistent memory is being used for my database. So what I wanted to look at was, if I queried data for my single table that used all of the memory, because my table is so much bigger than DRAM, by definition, I'm hitting persistent memory. So that's the worst case. If I looked at a small amount of data, say 40 million rows versus 160 million rows, I know via various calculations that 40 million rows would easily fit within DRAM. If all my data fits within DRAM, I should be getting DRAM cache hits. So it should be faster than if I'm querying all of the data, which is hitting persistent memory. So the point being, I was artificially varying how much data I accessed to see just how fast or how slow persistent memory was when running in memory mode. So it's all about DRAM cache hit ratios. So another way of looking at it, if I used all of the memory with an even probability using a random number generator from A is 0 up to the maximum, that would be the worst case. If I artificially constrain the rows, I should get a better cache hit ratio. So this technique I used, and I'm going to show you the results of that. I also did similar things with different distributions just to see if the type of distribution affected the results. The interesting thing was it didn't really affect the result no matter what distribution I used. And I'll come back to that. So the benchmark I was using, it's one of the standard workloads we had. It's been around for 20 years. So I tried it with persistent memory with 10 million, 100 million, and 1 billion iterations for each test. So I did many, many tests, and I'd take the average of each test. To get consistent results, I ended up using 10 million because if I used less than 10 minute iterations, I tended to have larger variance of the results. So I wanted very predictable results. I was getting about the same results for 10 million as 100 million. Obviously, doing 10 million iterations takes less time, so the tests were done with 10 million iterations. So there's nothing special about this code. It's all on GitHub. You can download times 10, try it out yourself. So this was the interesting result. I knew that persistent memory could be up to 3x slower than using DRAM. So I did my benchmarks and I got some numbers. and I couldn't really tell that I was using persistent memory, which surprised me. So I did a lot of digging, and I ended up having to create a histogram to figure out what was really going on. So this histogram is between 1 to 3 microseconds with increments of 1/10 of a microsecond. So when I used this histogram, I basically got 3 areas of activity. The first area of activity was at 0.1 microsecond. So we got hits there when we're hitting the L3 cache of the Intel Xeon CPU. The second area for activity was between 1 to 1.2 microseconds. So it turns out this was when I was hitting DRAM, and we were able to validate that with many other machines that we've used which didn't have any persistent memory. The third area was when I was hitting persistent memory. This was happening at about 2.1 microseconds. So I said PMEM can be up to 3 times slower. For the workload that I was doing on the hardware that I was using, it was about twice as slow. So let's just put this in perspective. DRAM is faster, persistent memory is slower. But what we're still saying is we're still doing primary key lookups in about 2.1 microseconds, which is pretty good. So if you take the average of that, it's about 1.5 microseconds. It's pretty good. So that is a data point. So that's using a single connection, just how fast can you do it? So the rest of the benchmarks I'm looking at is looking at throughput for reads or writes or combinations thereof. So this was a good starting point. Oh, this is the same data. There are other numbers in there. You just couldn't see them based on the scale. So when I accessed all of the data, or 1.4 terabytes of it, I was getting about 1 million hits in DRAM. If I had a much narrower range of rows, I was getting about 7x more hits in the L3 cache. Okay, so the point is there are other numbers in there, but these 3 spikes are what you could see in the previous slide. So what I'm looking at here is how well does persistent memory scale? And I'm artificially constraining the workload such that I can guarantee I'm only accessing half of the DRAM. So if I run it long enough, all of the data accesses should tend to be hitting DRAM. So I compare the DRAM only accesses on the machine versus DRAM cache hits on the same machine. And it turns out I'm getting the same performance. So with persistent memory, you can, via software control, I could put the machine in app direct mode and never use persistent memory, which means I could access the DRAM directly. So by running it in that mode or in memory mode, I could compare on exactly the same hardware, just DRAM versus DRAM with cache hits. So the point being, I couldn't measure the difference. There is slight difference, but it's a statistical noise. So I was nicely scaling up to 20 million queries per second on this machine. So that said, if your workload working set is so small that it fits within DRAM, there is no difference between DRAM and persistent memory. So that's a good result, and it scales. I did the same thing in this case with writes. So I'm guaranteeing that the working set is so small that it fits within DRAM. And I got basically exactly the same results for persistent memory and DRAM only. So that's a good result, and it's scaled. Now let's make it more. Then what I wanted to compare was, I just showed you the best case where I was guaranteeing it all fitted in persistent memory. I then looked at the worst case where I guaranteed that the working set covered all of persistent memory. And for my reads, that was taking about 1.6 microseconds. So that's the worst case. So that's 160 million. If I halve that, I'm still getting the same latency. If I halve it again, still the same latency. So it was only when I was getting really, really small that you could see the difference. So the best case possible was about 1.1 microseconds. The worst case was about 1.7 microseconds. So this wasn't necessarily what I expected, but it just shows how good or how efficient the Optane persistent memory manager is, because the latency wasn't really affected by the working set size. From worst case, the working set was all of the persistent memory down to virtually nothing. There was very little difference. That was for reads, same for writes. So this was a very good result. I was expecting, as the working set size increased, for the latency to be badly affected. It wasn't. There was an effect, but it was a fairly minimal effect. So that was all the best case results. Now I'm looking at worst case, the same read tests, but I'm forcing the data to access all the persistent memory. And it turned out I got exactly the same throughput as I did when I'd forced the data to all fit in DRAM. So I'm still getting over 20 million queries per second. So that was good. So what I'm saying is, even though I'm forcing the system to use all persistent memory, I'm still getting about the same performance I was getting as if it was all in DRAM. So we've got nice linear scalability up to, in this case for this machine, about 20 million queries per second. Likewise, if I have a read-write workload, I'm still getting the same throughput. In this case, about 2.5 million ACID transactions per second on this one new machine. I'm still getting linear scalability. I'm still getting the same throughput that I was getting with DRAM only. So these were surprising results to me, but very good results. So what I mean by that is, I basically couldn't tell the difference in latency or throughput of DRAM versus persistent memory when used in memory mode when I had a DRAM to PMEM ratio of 1:4. So I'm running a very simple workload. It's a very consistent, predictable workload, and I'm running it millions of times. But it turns out for our customers that use ×10 as either a system of record or a database read cache, that tends to be the sort of workload they're using. So I didn't know how much overhead persistent memory would have. So running it against ×10 with this very simple, predictable workload, I basically couldn't tell the difference between DRAM and persistent memory. That surprised me, but that's a good result. So what we're saying is persistent memory can increase our capacity cost effectively versus DRAM while still going basically just as fast. So let's look at how we can use it as a read cache for a database. So TMobile has a large system with 86 million users. Their existing system used an Oracle database and they wanted things to go faster. So they built a big Cassandra cluster, they denormalized everything, and it didn't work very well. So they used ×10 as a database read cache. So they went back to the original data model, went back to the original SQL, and the JDBC microservices, instead of going against Oracle, connected to ×10. So they just basically changed the connect string, and it went significantly faster. So using ×10 as a database read cache can really help things out. So T-Mobile used a 4 terabyte large machine. They, now that PMEM's available until persistent memory, they can do the same thing cheaper than if they're using DRAM only, using either a single machine or a cluster of machines. So obviously, times 10 does caching for the Oracle database very well. But via Golden Gate, you can also do read caching for virtually any relational database. So whether it's an Oracle or other database, the architecture is pretty much the same. Committed inserts, updates, and deletes are captured in the transaction log file. They're asynchronously pushed to the Golden Gate target, which in this case is times 10. So times 10 could be a single instance database, or it could be the clustered version, makes no difference. So by using persistent memory, if you do a little bit of math, you can figure out your maximum capacity. So with 64 nodes, we can have just on 768 terabytes of data cached with those microsecond response times. Very soon we'll add 128 nodes to double that. So if we double that, that would be 1.5 petabytes of data. So in conclusion, using persistent memory works very well with the times 10 in-memory database. Why? Because the Intel Xeon Memory Manager did a very good job of migrating the hot data to DRAM and the colder data to persistent memory. So it's easy to say, but it's hard to do. So I did all my benchmarks to see just how bad it was. It turned out it was really good. So by using Intel Optane persistent memory in memory mode, we're able to get basically the same low latency and high throughput that we could get for DRAM. So it's a very good fit for using times 10 in-memory database for SQL workloads. So whether you use times 10 as a system of record or times 10 as a cache for your relational database, it will dramatically speed things up because you get lower latency and higher throughput. So I found Intel Optane using memory mode to be very fast and cost effective. And as a net result, you can get up to petabytes of data for read caching. So that was my talk. So I'm open for questions, Terry.
All right, thank you, Doug. If anyone has any questions, please type them into the questions box there in the GoToWebinar control panel, and we'd be happy to answer any that come up. First question, Doug. So is this available for production applications at this point, or any customers using this?
Absolutely, it's available. So using Intel Optane persistent memory in memory mode is certified and available for production support today. So yes.
Okay, good. Any other questions, anyone? Let's see, a question. They're asking about cost effectiveness and any benchmarks you might have there.
Great question. So cost effectiveness, what I hopefully showed you in the benchmarks, like I didn't know what the results I was going to get. I had heard through research and prior testing that persistent memory could be up to 3x slower. So I wanted to try out memory mode to see, just how good or bad it was. I had no expectations. I was shocked by just how good it was. So the performance was basically just as good as DRAM. So if you look at price performance or cost effectiveness, if you're getting the same performance for a lower price point, that makes it very cost effective. Now the cost of DRAM, it changes day by day. Likewise, the cost of Intel Optane memory. Intel puts out its list price, but you tend to buy it from your favorite hardware manufacturer. So the point is, because the price of DRAM and persistent memory changes day by day, it's a moving target. But the tendency is that today persistent memory is cheaper than DRAM for large capacity, and the expectation is over time it will tend to get cheaper, because luckily Moore's law is in our favor. So hopefully Intel can keep increasing the capacity of persistent memory, and hopefully over time it continues to get cheaper. So it's basically just as fast now, it is cheaper, it will tend to get higher capacity over time, and it will tend to get cheaper over time.
Okay. Let's see, next question is, if you're using the DRAM, using DRAM as cache will make the DRAM space invisible to the user space. Is that correct?
That is correct. So that's got nothing to do with times 10. That's just how persistent memory work. When you run in memory mode, you can't see or access any DRAM. You can only access memory, and it's just a probability whether you're going to hit DRAM or persistent memory. So the larger amount of DRAM you have, the higher probability you'll hit DRAM, and also the working set size will tend to affect that proportion of DRAM to persistent memory. So it's, you roll the dice. I didn't know what results I was going to see. For my workloads, I got very good results.
Okay. Question, do you have any expectations on graph database performance?
None whatsoever. I'm a SQL database specialist, but at the end of the day, your graph database, with persistent memory, you're doing loads and stores, which is a fancy word for reads and writes. So you need to look at your data structures, what's transient, what wants to be performant. So it's really going to depend on your architecture and literally how good your code is. So if you have badly written code that sucks in DRAM, it's still going to suck in persistent memory. So there's research papers for graph databases. So if you do some Google searches, you'll be able to see what other people have done.
Okay. Question: if you ran the same test with no persistent memory but just DDR4, do you think the DRAM read-hit latency will be around 1 microsecond?
Great question. So it may not have been clear, but that's actually what I was doing. The same machine, I can reconfigure to only use DRAM. So if I run it in app direct mode and never access persistent memory, when I access memory, by definition, I'm hitting DRAM. So I did a bunch of tests in that mode. And then I reconfigured the machine to run it in memory mode. So I couldn't access DRAM, and I had to access persistent memory. The point was, I did all those comparison or baseline tests. I couldn't measure the difference between DRAM only versus DRAM as a cache for persistent memory. So that was for my workload. It may not be applicable for other workloads, but using a sophisticated SQL and memory database, doing primary key lookups or updates by primary key for a single table, the difference between DRAM only or persistent memory and memory mode, you basically couldn't measure the difference, which surprised me, but it's a very good result.
Okay, great. Well, we're at the end of our time. Thanks for a great talk, Doug. And everyone, the next talks will start in about 10 minutes. We've got one ongoing cloud native serverless applications with Ignite, and continuous intelligence applications that always have the answer with Swim AI. So thanks everyone, and have a good rest of the day.
Thank you. Bye.